attitude and there is an embedding.
Correct.
But does it construct for you?
Yeah,
The embedding process. It's not difficult to
No.
even a graph can.
For the in the what happened to the arbitrary
Arbitrary not possible. Even for quantitative it is possible.
No, even for arbitrary paper is not there. Djokovic is there. Djokovic is not the same as there. Same spelling, Djokovic. Theorem is different only. Some equivalence, some relationship is not there. It has been equal there. Only that. Only then is there.
But then now you mean that every vertex actually the one small information neighbors. It is equal to all the vertices. Then isn't it that
Okay. But see how there's no one person in the world. You don't know who. You should know everybody always here, but I think we have to relay the company. You know your contact. Your contact is there in that 12:30, so that we'll have 1.5. Yeah, will that be comfortable? What? Say that again? Okay. Yeah, it's a good thing. Because 1 hour is too short for life. Yeah. You go there.
So when do we start?
9 o'clock?
Yeah,
So half an hour proposal, I will confirm it and then let you know. Half an hour, we'll just push it ahead so that we'll get the gap in the middle.
1.5 hours for lunch.
We don't want to squeeze the breaks.
See, it's starting 9:15 to 11. 9:15 to 11, 11 to, yeah. 9:15 to 11, 1.5 hours.
Yes, sir. We'll start by 9 so that we can have
Do
the
10:30. 10:30 to 11. 11 to 12:30.
11 to 12:30.
12:30 to 2.
So I don't need to. Yes, that's what it is. I will inform you guys. Mostly we'll start by 9. That's I was saying I don't want to squeeze the breaks. Breaks are very essential.
Very useful.
Very essential to digest the things and then discuss those things. Very important. Okay.
Yeah.
So we start early. We'll get enough breaks.
what?
Huh?
Tomorrow.
No. I just what talk or lunch?
Both things.
Both.
You need time for the lunch also to digest so that 2 o'clock session will not be useless.
2 to 3:30.
You can participate or you can.
Just say tutorial and then we start.
Oh, just look.
Yeah, so I will do some problems.
Oh, yeah.
So maybe I will do this. Tutorial problems. I will do.
After the second time you
Oh. No, but it didn't write on it. I don't know how to use. Anyway. So I will do some 2-3 problems, but so I have some problems sent, but I will send it again. So is it clear? I'll just finish this proof and then I will go on to. So if your V is all ones vector, then what do you get by using this Schur complementing? So what is the determinant of this? I can maybe write it. So it is determinant of this minus 2 times identity, but n minus 1 cross n minus 1. Times minus let it be this determinant of minus 2 times identity into determinant of 0 minus 1 transpose minus half identity 1. So what will that give you? So here there's one more version. Complement. So D is invertible, similarly you will get. So both of these are easy. Okay. So if you were to use this version, determinant D, we have something similar. Okay, so with that M is so 0 B transpose B minus 2 times identity. So you apply this determinant of D into determinant of A minus this you'd have to this Schur complement. There is a book actually, Schur complements. It's so popular a technique that there's a book for it. Schur complements, I think Zhang. The author is some Zhang, I can't, who's in Zhang or something. These Chinese names are very tough. It sure is tough for them also, our names, but for us. So what is this going to be? If I zoom and then the font doesn't get zoomed, I have to. Yeah, that's okay. Yeah. So equal to, so determinant of 2 times identity will be two. So what will it give you? Minus 2 to the n minus 1 to n minus 1 by 2. So Komal says it's n minus 1 by 2. So huh? So you're saying you're agreeing with this, or both of them say? Others? You're also saying it's okay. Okay, Aditi is also good. You are THI or TI? Some people put. You. Here also some may have made the same mistake. No, I have a friend Aditi with that other THI spelling. So I think that's correct. So that's it. So you get which is what we want. And it's only a function of n. Yeah, it doesn't depend upon the tree. Yeah, this you try to convince yourself. The determinant of D is same as determinant of F because we've just done some row operations. That's it. Okay. All right. So this takes care of the first proof of this Graham-Pollock theorem. Yeah. So before I go on to the second proof, let me give some. See, there are a lot of gaps that I've said. So let me try to plug some of the gaps in the tutorial. Go to the mode. So I said that there is this Graham-Pollock theorem, no? That if you write a complete graph, you want to write it as an edge disjoint union of complete bipartite graphs, you need n minus 1. So complete graph Kn, if you want to write as a, the edges of complete graph Kn have to be written as a disjoint union of edges of complete bipartite graphs. You need n minus 1 bipartite graphs. So when we saw with n minus 1, you can do. I don't know if it is above or below. Maybe I will just. So you may see two versions of Graham-Pollock theorem. One is this for the tree. One is this for the complete graph. So, correct. So let me prove this theorem. Version of Graham-Pollock theorem. Complete graph version. So what does this theorem state? It states whatever. If you take the complete graph on n vertices, you want to write it as an edge disjoint union of graphs, complete bipartite graphs, you need at least n minus 1. So as I said, suddenly this they will use some algebra. So let me also go to sorry, I'm just not used to this. It moves suddenly very fast and suddenly very slow. No, no. Sorry, I'm just incompetent to this. Not used to this. Okay. Fine. So, so you know what we want to write. In edge disjoint manner in complete bipartite graphs. So as I mentioned, so this edges of the complete graph, I will write it as all the edges of the complete graph. There are how many n choose 2 edges in Kn. So I'm writing it as just this sum of monomials. Every monomial xi xj is the monomial corresponding to the edge I comma j. Yeah. So I want to write this as summation over d, not d, I. So this is the edges exit in the complete graph. So xi ti. Yeah. So if I say I going from 1 to d, so it will be u belonging to si. This is okay. So in bracket so that it causes more clarity. Is it clear? I want to write the edge set of the complete graph as a union of using in an edge disjoint manner union of edges of the complete bipartite graph on SITI. Yeah. So the number of i's, that is the d, is the parameter that we are trying to minimize, and we are claiming that d cannot be less than or equal to n minus 1. D has to be greater than or equal to n minus 1. This is what we want to show. So what does this theorem say? So we have it. Suddenly, logo also came. Don't do more than this. That's all. Maximum zoom. Okay.
Yeah, it's slow because it's the same.
It's the same page.
It's
There is an add symbol there.
This one.
New page there.
Okay. What is that thing doing there?
no, that's the mouse. Right?
Let me- Yeah. So then if this is what I want to show. This is the theorem statement, yeah. So this is the move it a little down. Yeah. So let's see the proof. So I can write the sigma xi xj as sigma xi the whole square minus what is the left hand side can be written as, so I'm saying sigma xi the whole square, not sigma xi and minus the half I have to put, huh? Yeah, I may have to put the half, yeah, for the this is the LHS. So now suppose your d was less than n minus 1, less, then d is greater than n minus d, correct. So to the contrary, d was strictly less than n minus 1. So if my d was strictly less than n minus 1, so I'll come up with a contradiction. Yeah. So what will I do? Consider sigma xu you take this and you also add so you look at this here, how many terms are there? There are d terms, and I'm choosing the, so each of the d terms is of the form some product on the left and some product on the right. I'm only choosing the term on the left hand side for the side. Yeah. So how many such equations are here? There's one for every I now. So there are d of them here, and how many such? This is one extra. So how many variables do I have? How many equations do I have? I have d plus 1 equations. So I'll say it and then I will write it. So I have d plus 1 equations and how many variables? N variables. So suppose my D is strictly less than n minus 1, then D plus 1 is strictly less than n. So number of variables is, sorry, number of equations is strictly less than number of variables. Yeah, and I have a homogeneous system of linear equations. How many variables? How many equations? Let's just recap once more. D plus 1 equations, and now D plus 1 is strictly less than n, but number of variables is n, which is strictly more than number of equations. So there is a non-trivial solution. But then what will happen? Left and right hand side will become, so this is satisfied, this is one of the things. So there is a non-trivial solution. So some xi is at least, and over reals you get non-trivial solution. Non-trivial solution over what? Over what? What field? Real. You can get over real. Yeah, you don't have to go from real. All equations have real coefficients. You don't have to go outside to some other. So I can get a real solution, non-zero solution. So what about this? Right hand side, what is going to happen? This term is 0. So this into something 0. So right hand side is 0 because this is one of the constraints I am putting. Whatever is there here, I am putting here. So my non-trivial solution will satisfy sigma xu u in Si equal to 0. So all of this will be 0. The first term is 0, so in 0 into anything is going to be 0. You add 0 some number d number of times, it's going to be 0. So the right hand side is 0. What about the left hand side? Why this? This is 0. This is non-zero. Xi squared. So I have a contradiction. Where is the contradiction? Because d is less than, strictly less than n minus 1. Here. So let me say it once more. I have to give a contradiction for d greater than or equal to n minus 1. So that means assume d is strictly less than n minus 1. Okay. So d is strictly less than n minus 1. I am going to set up a system of linear homogeneous equations. How many equations? D plus 1. So d is strictly less than n minus 1 means d plus 1 is strictly less than n. So the number of equations is strictly less than n. How many variables? N. So there will be a non-trivial solution to this homogeneous system of linear equations. Non-trivial meaning non-zero, yeah, and over reals. So what will happen to the right hand side? Right hand side will all be 0 because each of the factor here is 0. Each factor here is 0. So you just plug in for x, you plug in here. Each of them will be 0. So it has to be 0 into something. So it is 0. Each factor is 0. You're adding 0 d times. So it will be 0. Right hand side will be 0. Left hand side will be by this. This is the same as this. So this is 0 because that is also one of the constraints. Sigma xi equal to 1 to n. So this is 0. What about this? It has to be non-zero because you have at least some of the xi's is non-zero. So xi squared if you add, it will be strictly positive, minus that's okay. Positive, negative. It is non-zero, that's all I care. So this is non-zero. So left hand side is non-zero, right hand side is 0.
The solution we need is just any real solution.
Yes.
Or some non-negative solution.
No, non-zero real solution. Non-trivial zero solution. I only care for the solution to be some xi has to be non-zero. If some xi is non-zero, the left hand side will be non-zero, right hand side will always be 0. Let me say it. Let me write down. I don't know what I did, but I don't know, I lost it. I need some help, sorry. No, I just don't know, the moving when it's zoom, no? Yeah, second page. Yeah, I'm also trying, so I have also done. So it seems to say, this icon seems to say that.
Pages. So yeah, maybe.
Huh?
Pages. Over in the top, here, the second page. Why is it black?
I don't know. Or maybe let's go to here. Oh, no, okay.
No,
I know.
You don't think so, the second page only.
I think so. Did I write in the first page? No. No, maybe I moved, that's why it's not able to show you the area. See, this move causes me some trouble now.
Whole. It should be there. So this also whole.
It will only show the last portion, I think.
So on that side, so see the line.
Yeah, it's that way.
So,
Okay.
and now so.
Zoom out.
Zoom out.
This is
Not
massive.
working.
Okay. No, huh? Okay, I will have to write it again. I will do it again. It's not a problem for me. No, I'm just sorry. I don't know how to use this. Yeah, chips.
Yeah, I don't.
Okay. Go to this. Yeah, okay, suppose I move it here. So then what do? Maybe I just scrap this and start writing again. With that I can do. Because then if I write here and then how do it get projected? Oh, okay. I am okay with it. This is I have not used. I have some Samsung tablet, which is very similar, no? Yeah. This is even better. Then better than this. But is the proof okay? Many people are convinced. So it's a good proof, remarkable proof. The statement is purely graph theoretic. Pure proof is just some algebra. No, and I don't know any non-algebraic. Many people have tried some computer, some counting, something they'll do, but what they're counting is also some algebraic. So it's not.
Yes.
Yeah.
With the theorem, the proof is clear to me, but let's write it algebraically, somehow does clear to me. So the theorem relates total number of edges in the complete graph. When you write it as a union of bipartite.
Yeah. Thank you. Yeah. It's very key.
When you write it as a union of distant bipartite graph, then you find a lower bound for number of graphs. Right? So in the left hand side, when you write summation xi actually, that is number of edges, right? When xi are vertices, xi actually is an edge, right? That represents edges. Xi actually is an edge, right? And then the right hand side, when you have a summation of products, so xi are vertices in your si set, and those xb's are vertices in your 2i set.
Correct.
Then when you do product, you are counting the
every edge which is
edges, right?
because it's a complete bipartite graph. All the edges on the complete bipartite graph will appear exactly once.
Cross product represents an edge, right? For each.
Correct. Every edge of K, Si, Ti will be appearing once in that product. That I'm just, instead of writing it as sum of edges, I'm writing it in as sum into some other sum.
So that's just a representation of edges in terms of the x-axis, right? And how are you treating that as numbers at the end?
As variables, are they okay?
Yeah.
Then
xi is a variable, right now in my.
no. Xi is a variable. Xi xj is xi into xj.
But that is edge, right? It represents as an edge.
So xi xj is a variable. Xi xj is an edge for you. Then xu xv is also an edge, no?
Yeah, but then.
So as variables, this is okay. Then I can plug in. If you have some identity involving variables, I cannot plug in some 1, 3 and all in the variables. Then I'm getting 0 equal to non-zero.
No, there's equality I'm worried about. Summation x equals summation is same as summation xi squared minus summation of xi squared. That equality, because they are not numbers. Xi is not a
No,
product.
that's no is an identity, no? It's an identity over variables. Sigma xi is the whole square. What is that?
That is a number.
No. It's true. As long as the variables commute, it's true. You only need commutativity. Otherwise, you have to write xi xj and xj xj have to be written separately.
Okay.
As long as the variables commute, it is true. Yeah. Any other questions you can ask me? Yeah. Yeah.
In the theorem, with that summation of the
Yeah.
What do you mean by summation of it?
What do you mean by summation of it? Say that again once more.
summation of edges.
See, every edge I'm writing as xi xj. Okay.
Xi xj represents your vertex.
No. Xi represents vertex.
That's what xi. They all are vertices.
Correct.
Xi xj is the edge between vertex xi and the vertex xj.
Vi and the vertex vj.
So what do you mean summation of that edges?
So when you're saying all the edges in the complete graph, that I can write it as every edge appears once in the complete graph, appears once in this decomposition as a sum of bipartite graphs. If you agree to that,
Summation of
It's a formal variable.
yeah, it's a formal variable.
So variable of the you can think of it as a variable inside the
Oh,
polynomial.
wow.
So it's not a scalar.
No, it's not.
It's a variable. That's why I'm plugging in values. If I don't have variables, I can't plug in values. Only thing is commuting variables. I have commuting variables x1, x2 up to xn. Xi, xj denotes the edge ij. There xu, xv denotes the edge between u and v. So now if I want to write all edges of the complete graph are written exactly once. So then I'll look at sigma xij over all edges of the complete graph. Written once as every edge appears once in the complete graph. That's what is depicted on the left hand side. Appears once in the right hand side. That is depicted as sum over all the d k si ti. So every edge occurs only once. It's an edge disjoint decomposition. So this sum is the sum of all the edges in the complete graph on the left hand side. This sum is the sum of all edges in the D complete bipartite graphs.
But if we take, I'm taking two edges, say x1, x2, and say x3, x4. So what will I get if I sum these two edges?
What will you get, me?
Here we have summation of edges.
Critical meaning is not.
Yeah, that's what. There is no graph theory. That's the point.
Critical meaning is
Just
Yeah.
a polynomial which contains which encodes the information of
Correct.
the graph. If you have vertices x1, etc., etc., whenever xi xj is an edge, you write a term of the form xi multiplied by xj. Okay, so when you see this polynomial, when you see x1, x2, you know that 1 and 2 are adjacent. When you see x1, x3, 1 and 3 are adjacent. If x1, x4 is not there, then 1 and 4 are not adjacent. So it is a way of encoding the graph as a polynomial in n variables. Like
So we have D plus 1 equations in n variables. Xi. So if D is strictly less than n minus 1, this is the same as saying D plus 1 is strictly less than n. Yeah, the star. Yeah,
That star will be vertex.
which star?
The star will be vertex.
The D plus 1 equations.
I understood you have D plus 1 equation.
Yeah.
How do you got that constraint?
How do I get which constraints?
summation of.
No, because if you are able to write it no, as a sum of, you are able to write it as a sum of D complete bipartite graphs. So then I can, the one on top, that's okay. So there will be some SI and some TI. How many SIs do you have? D of them. So you add all the D of them, which is this first part. Then you add this one.
I'm asking how do you equal this? How do you equal this?
No, I'm putting equal. Consider the following system of linear equations. Consider, I should say, I don't know what is written. Consider, I want to say consider. So, how do I use eraser here? Here it is. Consider. So I will say consider equations. Yeah,
Can we use this linear algebra here? Because these are defined vertices, right?
correct. We are using linear algebra only. I mean, what are we? Ultimately, the argument is linear algebraic. It says it's
But how we use
Solutions have meaning. Because once
The
I
vertices can be numbered x1 to xn. That may not have the only representation.
correct.
But when you solve it using linear algebra, those xi is taking some values, that has a meaning.
Yeah, sure.
But then how, that's what, it all depends on the representation of those vertices with xi.
See, anyway, the graph is labeled. No, complete graph is labeled.
There is a
Where just
graph, when you label the graph vertices with xi.
yeah.
That those values have got no meaning.
The xi, if you label the vertices using xi, then
It's better to label the vertices as 1, 2, 3.
yeah, maybe 1, 2,
And
3
reserve the exercises.
variables corresponding to the word. So xi is the variable corresponding to the vertex, either vi or I, how you fix some. So now what is your question?
The contradiction that you get.
Correct.
Here you have the linear system
Correct,
and you say it's got a solution.
correct,
That's how you're contradicting.
correct.
But I'm saying graph theory, the graph part has no meaning for those solutions.
No, because I'm using these no to
But here the summations have no meaning. That's what I'm saying.
summation has
No meaning.
no summation is one portion. This summation into that summation has meaning. That cover all the edges in the complete bipartite graph between SI and TI. Because I don't want to write mod SI into mod TI terms, I'm writing it in this manner. This is just some shorthand way of writing. See how many edges are there in the complete bipartite graph? When you have SI is a set, TI is a set. So mod SI into mod TI, that many edges I have to write. Just like I'm writing it here, XI, XJ, I have to write that many. But instead of writing it mod SI into mod TI terms, I'm writing it in some slightly different manner. Yeah, I know this proof causes a lot of suddenly mysterious.
Also, when you're considering the equation. Summation of the edges. How can you equate it?
No, summation of the edges, summation of the vertices. Xi's are all
Sorry,
okay.
summation of the vertices.
Correct. No, I can equate anything to 0. What is the problem?
Right, suppose you have a formal power series. Suppose you have your generating functions in formal power series. So suppose you equate two formal power series, no matter how you have written them. Okay, so this formal sum is equal to that formal sum. But if it is true in that form, then for every substitution of the variables, same substitution when you do on both sides, this number should be equal to that number. So here they are just formal sums initially, but then as a trick, we are substituting some values and showing they cannot be equal, which means the formal sums cannot be equal as well. Like if I have a function g of x which is expanded in one series, some f of x which is expanded in another series, you claim that these are equal. Then I say if these are equal for every x, then g of 0 should be equal to f of 0, or g of 1 should be equal to f of 1, although they may not have any meaning, but they should be equal. So this is just a trick where we substitute particular values by finding some solution which exists, and then saying they cannot be equal. Yeah, yes. Yeah, exactly.
No, here I'm getting a thing where they are different. No, you can set values xi such that they both give you the same. But that doesn't give me a contradiction. To show a contradiction, I have to give you some evaluation to the variables.
Yeah.
Yeah.
Some assignment.
Some assignment. What the assignment I still don't know, because the general theory says there exists a non-zero solution. But from that you can infer that if you evaluate, if you plug the xi to be equal to whatever that non-zero, non-trivial solution you get, non-zero solution, then you will get 0 for one of the sides and non-zero for, yeah. So the left hand side will become non-zero because it is this. So plugging in. Okay, so I'm claiming if you look at 1, so 1 will, all terms in 1 will become 0, whereas you plug it in 2, this. Pointer? There is a pointer, is it?
Oh, no, that's no longer there.
No longer there, okay. Okay. So this term will become 0, this will become non-zero. Whereas all of this will become 0. So this 1 will vanish, 2 will not vanish. What?
If there is a laser function in that, you scan your.
No, that's okay. No. Okay, sure. This is good enough now. If I don't go for this, I will be happy. That itself is there. Yeah, is it okay? So let me see. Yes. So those who are still not convinced, yeah, you can still, yeah, you can discuss anyway. That's okay. So what I'm saying is, you take the formal sum of all edges on the complete graph. You can write it as a sum of edges in the complete bipartite graph, and you can set up a linear homogeneous system of equations which has a non-trivial solution. Okay, so that takes care of this Graham-Pollack theorem for complete graphs. So you need at least n-1 bipartite, complete bipartite graphs, and with n-1 we can do. So if you remember, we've done it. You look at k1, like 1 to everything, 2 to everything greater than 2, 3 to everything greater than 3. Yeah. So you do that, you will get n-1. So you need n-1, you can do it with n-1. So it is exactly n-1. Yeah. Okay, so this is okay. So this takes care of the Graham-Pollack theorem. And I wanted to do the second version, which is using this, it's called there is this method for evaluating the determinant. So it goes by the name Dodson's condensation rule, also called Jacobi. So this I thought it was Desnanot, but somebody said no, you don't know how to say it. It's a French name. Maybe there is some Denano or something like Viano. So I don't know. Don't ask me the pronunciation, but something like that. Okay, I'll tell you the theorem. Don't ask me the name of the person who found it. That's too tough. So I will use this notation to denote the submatrix of A that you obtain by deleting the ith row and the jth column. So if I want to delete 2 rows and 2 columns, I1 j1 row and or I1, I2 row and J1, J2 column. Then I can also write, so for example, A, I1. So I just, I can put a notes, submatrix of A obtained by deleting rows I1 and I2 and columns J1 and J2. So this notation I will just use. I will extend that, just put a comma and make it into a list just for. Okay. So A is a submatrix, that's all I've done. Then determinant of A into determinant of here there must be an undo. No? Is there an undo? Yeah. So who all know this? It comes up to all those know. Don't worry. If you don't know it, don't worry. I'll tell you. So there's a 2-page paper by this Doron Zeilberger where he gives a proof of this. So 2-page. So I will say, I will send you the link. So you please put in the WhatsApp group. So is it clear what it says? So you take determinant of A into determinant of A, but you remove first row, last row, move first column, last column. Yeah. So this is a n cross n matrix. This is n minus 2 cross n minus 2 matrix. You take determinant of this, multiply it with the determinant of this. Then that is determinant of A, 1, 1, n. So, okay. So this I will not do. I will ask you to read this 2-page paper of Doron Zeilberger. So using this is called condensation rule, also called Jacobi Tenano or whatever. Tenano. Yeah. So I will use this, and I will also try to find some. So we'll use result to give an alternate proof of the Graham-Pollock theorem. So remember, recall theorem. So Graham-Pollock they have two. One is for the complete graph. One is for the distance matrix of trees. T. Take its distance matrix D. Then determinant of D is with this I want to give an alternate proof. Yeah. Sorry, I'm using your tablets. You want something?
No, was it okay?
Yeah.
I don't have techno.
I'll give you. Yeah. I'll give you this. It's good. So I will give an alternate proof. So consider a tree. So I'll assume 1 is a leaf and n is a leaf. So every tree has at least 2 leaves, no, that much we know. So maybe something else. Let T be a tree. In vertices, and let vertex 1 and vertex n be leaves.
Pull up and hold.
What?
Just pull up the new page.
Pull up.
Yeah. Oh, yeah.
Alright. So let vertex 1 and vertex n be leaves. Okay. Why am I doing that? Because if I delete vertex 1, then I will get a smaller tree. If I delete vertex n, I will get a smaller tree. So by induction, A11 I already know. ANN I already know. A1, n, 1, n. This also I already know by induction. Right? So let me give you an example. So if you have, so let's say so I have something like this. So if I delete vertex 1, I will get a smaller tree. If I delete vertex 5, then also I get a smaller tree. Yeah. So if in this result, this I want to evaluate determinant of distance. I'm going to apply this A to be the distance matrix of a tree on n vertices. So if I delete vertex 1 and vertex n, that is row corresponding to vertex 1. So row 1, row n are deleted, column 1 and column n are deleted. Then again I get, see this distance matrix, if you delete a leaf, what you get is a smaller tree, and the restriction of that submatrix is actually the distance matrix of the smaller tree, right? That's what we will use. So if this determinant of A minus row 1, row n, column 1, column n, that I can get by induction. Here, determinant of the distance matrix of A, where you subtract, you remove the first row and the first column. That is also obtained by induction. Nth row, nth column, obtained by induction. First row, nth column. Now, that's not easy. So if you look at the distance matrix, of this, you remove first row and so if you look at 1, 1 to 2 is 1, 2. So if you remove the first row and the last column, so if you remove this, first row is gone and last column is gone. So it's not even a matrix which is symmetric. So now everything goes, but you have to live with it. Yeah. And if you remove last row and first column, so that also is there. You remove. But are these two matrices? Do you have two distinct matrices or are they related? If you look at this, so in this, change the color. This is easy. These two are easy. Here, are these two different matrices? A minus first row, last column. A minus last row, first column. You remove at least, are they, if they are related, then at least we have. So in this equation, this is not known. These two are, looks like, no, these two are, all these three are known by induction. So by induction, this is not known. These three are known. These, are they two or are they one? Firstly, you tell me that. One guy is saying one. What is your name? Shashwat. Shashwat is saying they are related. It is enough to know one. So what is my question? How many things are unknown in this equation? So already this is unknown, but this is what we want to do. These three are known. It looks like there are, so one unknown, second unknown, third unknown. But I'm asking whether the second unknown and the third unknown are somewhat related. So if you remove from a matrix row 1 column n, let's say you get some other matrix P. If you remove row n column 1, what do you get? Because M is P transpose maybe, but determinant M is determinant M transpose. So for determinant computations, correct. So what Shashwat is saying is, it's fine. So there is only one unknown here. So we have from this equation, we are almost done. Excepting the trouble is there are two unknowns but one equation. So then we cannot solve. Two unknowns are there. So you need one more equation. You have two unknowns and two equations you can somehow solve and get. So in this, by induction, condensation, by induction, you know, determinant of D of D and determinant of. So you remove these two, these all of these, Further, determinant of okay. So why is this so? This is what. So contact Shashwata. Tell me your spelling. I don't know. SHA SHWATH. Okay. So you ask Shashwat. Yeah? So now we have. So thus we have one equation and two unknowns. So somehow if we can get one more equation involving the same two unknowns, then we can hope, yeah, to get a solution. Yeah. So what do we do? I'll tell you what we do. So in your distance matrix, no? So one is a leaf vertex. So who's the neighbor of one? The neighbor of one is, in this case, 2. One's neighbor. And who's 5's neighbor in this case? Is 4. So in general, suppose P and N's neighbor is Q. Yeah. So suppose you do column 1 is column 1 minus column P. So then what will happen? Column 1 is column 1 minus column P. So what will happen? So in this case, so column 1 will become, what will it be? I'm claiming it will be minus 1, 1, 1, 1 transpose. So it's a column vector. I'm just writing it as row vector transpose for space considerations. But is it clear? It will be -1 in the first coordinate, and why? Because of the same thing. Distance of any vertex I to n to from distance of any vertex I to 1 will be distance from I to 2 plus 1. So for everything other than this, 2 onwards. So this will be 1 more than this. So if you do column 1 is column 1 minus column P, yeah, in general I will do column P, I will get all the entries except the 1th entry. It will be 1, 1, 1, 1, 1. This is what we saw earlier. So we saw this column 1 will become 1, 1, 1, 1, but the topmost entry will be -1. Yeah, this is what I'm writing. So column 1 prime, I'll write it like this. And similarly, if you do column n is column n minus column q, what will the last column be? Similarly, it will be, yeah, 1, 1, 2, correct. Yeah. Okay. So actually, I'm not going to do this. I'm just right. This is all for things. So I will only do one column operation. Yeah. So all these are just for our own intermediate. So actually you do column 1 prime minus column n prime. So what do you do actually? If you do column 1 prime minus column n prime, column 1 equal to column 1 prime minus column n prime, what will you get? So because now do. So you can actually do only one. I only want to do one column operation. Yeah. These are just for our now. Start with, so restart with T and do column 1 equal to column 1 minus column P minus column n minus column Q. That's all I wanted. Yeah, just restart. No, the restart is important. Yeah. So now only one column I'm changing. This I did it just so that it's easy for us to understand. So what will column 1 prime be? So it will be actually, I'm doing this minus this now. So the first entry will be -2. After that, 0, 0. Yeah, penultimate entry is also 0. Second last entry. Last entry will become 2. Is it okay? Only for this, I just wrote these. I don't need it actually. So now, what is my D going to look like? So the first column will be -2, 0. Whatever is the same column. Huh? So now if you expand determinant by the first column, what will you get? Correct. So D11. That's what I'm putting in our notation. But this I know by induction. And now I have to do my. So what is the sign? Correct. -1 power n. N plus 1, n minus 1. One of the two. You have to put. N plus 1, n minus 1 both are okay. N1 first. Okay. So this I know by induction. So I have one more. So D and Dn1. So I have this. This is my first. This is my second. And of course, what is the second equation? Okay. And similarly, I have determinant of T equal to into. So this is actually -2. So now you have to be careful. So this term. And earlier I had determinant of this into something smaller equal to something minus n1. So I have two equations. So you look at the other thing that is obtained from this condensation rule. Only thing is it's a little more complicated because there are lots of 2 power minus 1 power n power and all that. Now you have to be careful. So now you have two equations in two unknowns. It's all. It looks like there will be a quadratic, so maybe there are two choices, but one of them has to be wrong. You have to see that also can to solve there are two equations. In fact, this is the other thing. So this is what is called as see if you look at okay, this is done. So this is the at the level of concept, the concept this is done. You have to work out some details. So you can try this. You working out some details. This maybe you can. It's not hard. Anybody has any issues till now? I am claiming the second proof is done. Improve done meaning modulo some details. Some work you have to do. Once you do it, this you have to do. Yeah? You can do it. After dinner, when you go back to your room, yeah, you just take your pad and push. So this Halmos says, you read this Halmos's book. It's called Automathography. I want to be a mathematician. It's a good book. Those of you who it's there. Paul Halmos, all of you know. The books he has written finite dimensional vector spaces. Then one problem book on linear algebra. What is it called? How to solve that is polio. This is Halmos. See, Halmos, what is the book on problem book on vector space on? There's a problem book that he has on linear algebra. It's very good. Of course, he has one on measure theory. He has quite a few interesting. He's a so in that he has automathography. So he says so all exercises that he knows. They're all of two types. One is pencil pushing. That is, you have to push the pencil, you will get the answer. One is the other one is mind expanding. You hear it, you get something. So this is all pencil. Now we are done. Pencil pushing is to be done, maybe. Not more than that. So if you are not pencil stylus pushing, you want to use pad, you use that. So in his time, he cannot say anything other than pencil pushing. But now in our time, if you want to expand it to include some other gadgets, yeah, you can include them. But essentially, you have to push the pencil, not much. Idea level, we have done. You can work out some. What are you saying?
This is also pencil.
Yeah, okay. No, Apple pencil. Okay. Yeah, pencil pushing. Yeah, so using the word of almost, yeah, you push the pencil, you will get. Yeah. So mind expanding and pencil pushing. Yeah, you remember the words. You good too. Okay, so that takes care of this. So in the first, have I left anything else? Any of the gaps? I try to fill some of the gaps. I want to be a mathematician. Yes, yes. He mentions this. So yeah, he mentioned several interesting things. That is, when he moved to some Michigan for some sabbatical, so he wanted to. That time his doctor said, no, you have to decrease your weight. So then the doctor said you have to walk. So he drew his big map you get now, which is drawn to scale. So he looked at the department office where the department is somewhat big. There are some 3-4 buildings. So in which building he got an office, he went. He was staying in some guest house for 1 month, and then he he got this map, drew a circle with his office as the center and radius 1 mile, and then radius 2 miles. So in that annulus, he looked for houses. But then he will walk in the morning, in the afternoon he will walk back home, and then after lunch he will walk back, and then again in the evening walk back. So 4 walks per day minimum. That's what he said. So he has interesting things. So that map is there. You can see some maps may not be accurate now because new buildings may have come. All that is, but then that map is there. So and there is a manual drawn. And then even where will he search for house? That also is. So it's just for fun. I mean, they work. And some doctor says no, you have to walk. And then he asks how much. Then this doctor says some 3 miles something per day. So he says okay. If doctor says 3, I will walk 4. So he says that So minimum that is it. You can read it. It doesn't have technical math. So he says his advisor von Neumann. So the first time he solved something, he told his advisor, yeah, I solved it. I said, very, very good, we'll write up. So advisor gave some problem, he did something. And I said, oh, if you can do this, then we can do this. Then he said, oh, so eventually paper expanded. So they both had. So it's a joint paper with his advisor. So then, so advisor said, okay, send me the write up. So it was written. And then he said, he saw this, von Neumann saw it, so many things correction, you just by his hand corrected. So in one place here, so for once and for all, we solve this problem. So that the advisor struck out saying. Then he asked him, no, but it's correct. Said, when you solve a problem, you solve it, you write the solution and go ahead to the next problem. You don't say once and for all, twice and for all. No. So he said that is not. And von Neumann, who is also legendary mathematician, he said, no, don't write all that. You solve the problem, go ahead. So that's many things. Okay, so what are the other gaps that I left in the first lecture? So I'll try to fill a few of them. Yeah, here in your thing it will be there. Yeah, so Dijkstra. So somebody can do algorithms if they want, or see Dijkstra, there is one all pair shortest path. You can use some Floyd version, that's better. So both of these, no, the tree, the n-1 is the number of negative eigenvalues. Yeah, it has one positive, n-1 negative eigenvalue. That's why it's n-1 in the tree. For the complete graph, the distance matrix is actually equal to the adjacency. Because complete graph, adjacency matrix, distance matrix is same. Because all it's just j minus I, is it? Yeah. All ones minus the identity. That's it. So the eigenvalues for that also there are n-1. What is that? That is like j minus I, no? So j and I compute. So if you so it always has 1 n-1 negative, 1 positive. Correct. So that also because the number of eigenvalues is negative. So if you use this Whitson-Huygens theorem, that there you will get n-1 in both. Where is Whitson-Huygens? Here. So if you take maximum, it will be n-1 in each. That's why you get both. Okay. Then, so now if we want to do some other things, maybe how much time do I have? Can I go for what is it? When do we have to stop? Okay. No, maybe.
No, if you want, you can go for 5 minutes.
No, it's okay. If I start, then I will not finish quickly. That is my worry. I have to do something, and I don't want to do that. So maybe I'll stop now. And so if you have any questions about I want to know this, tell me. Because I will also have to. I will know, no, people are more interested in algorithm. I can make some remarks. So yeah, till then I can. Okay, thanks. So then if people say no, I'm interested in, so depending on that, no, see when I learned music, no, I was like that. I learned Carnatic classical and I was a young boy. Now I don't. So that time I teach every certain mistake and all is very tough to get. Now you can get now YouTube, you go, the thing is there. So that time was very tough. So you have to go to the 3 lessons per week, but only 2 you will learn. One you go and hear because they have such a collection. They will play. And then they will say, oh, this guy seems to like these. So I will teach him these. So it's like that. So it will be slightly tailor-made for that person. So what I learned will be slightly different from my senior, slightly different from my junior, everybody. But that's good actually. See what you want, no? Syllabus, you cannot put one syllabus for some 120 people. It's not fair. Slightly different, something at least. Actually, if you ask me, no, every person should be treated separately. but that's too much work. So some amount is okay, but at least I will learn. I would like to do what was done to me. That much I can do. So if people say no, I want to learn some algorithms, then I tell you read this. If you say I want to do some algebraic, I tell you read this. If you say something else,
You can go for 10 minutes.
okay, good. Maybe. So I will tell you some results, and then maybe I will prove it tomorrow. So this. So this. How do I write now? Maybe I did something wrong. Now it's just scrolling. Oh, okay, okay. Yeah, it's not writing. That's the thing. Ah, okay.
5 seconds.
Oh, wow. Yeah, yeah.
We are in this tenure. And it is in the mainstream.
In which? In which?
In the earlier group.
In the earlier group, yeah, yeah, yeah.
Assume that it's a tenure. Then we assume that after reducing the evaluation is pending.
Correct. No, no. I'm saying whichever is better, you can. No, no. You can. No, no. You can firstly you form the tree backwards.
Yeah.
Delete one pendant, then another. Then at every time there is a way to do it such that you can reorder only within this also. N minus one.
Ah, that's what. So
Ah.
this one's neighbor doesn't have to be pending after prediction.
Correct, correct.
Because there may not be.
Correct, correct. So you can just do a unitary change, permutation change here, and identity tensor this, and identity direct sum permutation. That you can do. Now I can use. Thank you. I'll place it. Okay, okay. Maybe that's another. So now we know. So we know this matrix, distance matrix of a T. So see this distance matrix of a tree, no? So these are all what are called. So now they are isometrically. So there is this class to studied by Schoenberg. So Schoenberg studied metric spaces which are isometrically embeddable in L1 space. L1 space meaning let's take Rn but equipped with the L1 norm. L1 norm is the yeah one norm, that is taxi cab. What there's a name for it? Taxi cab, yeah. Taxi cab metric, yeah, correct. Correct. So isometrically embeddable, you know. So Schoenberg studied. And then Schoenberg proved in general, and the examples he constructed are very convoluted, but now we have no trees. See, when he studied, Schoenberg did this in 1938. 1938, the graph theory known is not very well studied. So this Graham and Pollack is 1971. Yeah, the Schoenberg is 1938. So he showed if your metric is embeddable finite metric. So you take a finite metric, so you can represent it as a distance matrix. Yeah, it has zeros on the diagonal and it's symmetric and it has satisfies triangle inequality. So finite metric space is meaning finite metric on a finite set. So zeros on the diagonal, symmetric because Dij is Dji and it satisfies triangle inequality. So if it is embeddable isometrically in L1 space, that means such that distance of Dii is 0. Dij equal to Dji. and Dij plus Djk. So this is called a finite metric. So he studied these finite metrics which are embeddable in isometrically in L1 space, and he showed a remarkable theorem that all such finite metrics have one positive eigenvalue, and that's it, one positive eigenvalue depending on the rank. Sometimes, so rank will not be, it may not be full rank. So if the rank, if it's a full rank matrix, R cross R matrix, one positive, R minus one negative. Sometimes the rank may not be full. That you can even see from. So as an X, so maybe I give an exercise. So construct a graph G whose distance matrix is singular. So connected here to you don't want graph entries of the distance matrix to be infinite. So you can do this. I'm saying you take even 4 or 5 vertices. Try. Not much. So don't try tree because the Graham-Pollack theorem will tell you it is not possible. You want singular. So you can try to do this. So this theorem of Schoenberg. This proof I will not do because it's somewhat technical. And Schoenberg, that 1938, the techniques he had, with that he is given. There is a slightly better proof, but if you want, I will say you read the book Geometry of Cuts and Metrics. The book. Geometry of Cuts. So what this says is that if you have, so I'm claiming if you're able to embed isometrically in the hypercube, then you can embed in L1 space. Why is that? If you're able to embed any graph isometrically in the hypercube, just the L1 distance. There, you say embed in L1 space, the coordinates can be anything. Here I am not saying coordinates can be anything. Coordinates are only 0, 1. Having distance coincides with the L1 distance. So isometric embeddability in the hypercube is stronger than isometric embeddability in the L1 space. So let me say it again. Which one? No. L1 spaces, there are some metrics which are where you need the entries to be not 0 and 1. Complicated. There are examples. I will give you. I will give you reference where to look at.
It's not possible.
No, I'm saying one of them will. Corners is not wrong. Corners is not. I can give you counter examples. Yes. So, what did I do? So, some graphs, for example, trees. So I said trees are isometrically embeddable in the hypercube. Yeah. So this you can try to do. So maybe I will do it in the next. That is next tutorial. I will do. So trees. in H n minus 1. In fact, you need n minus 1 dimensions. So I put H sub d or H superscript d? Superscript. No, I don't know. So if you tell me, then yeah, I don't know. Please tell, because I can either put here or no, because I'm not able to remember. Yeah, so it may be subscript only. Huh?
Dimensions only.
Yeah, maybe, huh? I don't remember now, but yeah. Check, huh? And I'm saying if it is embeddable isometrically in the hypercube, the hypercube is isometrically embeddable in L1 space. Why is this? This is obvious. Here, Hamming distance equals L1 distance. Because if you are here, your images are 0, 1 to them. So if you have only 0, 1 vectors, you think of just those vectors as vectors in R power. Here it's n minus 1, but it may be d. So if your hypercube, you had hd 0, 1 to the d, you think of those as elements in R to the d, and then the Hamming distance will be same as L1 distance. Yeah. So no, that is you. So x1 to xn, y1 to yn, distance is mod xi minus yi. You sum over I. Oh yeah, that is your thing of L1 spaces. No. Here, see, like a Euclidean distance is if you have x1 to xn, y1 to yn, xi minus yi squared. You sum over all, then it takes square root. No. Correct. So now you take the square will take care of that. Each component is non-negative. In general, it may not be. If you take L1 now, you take xi minus yi mod plus x2 minus y2 mod plus dot mod. Just that mod. You don't know square root, nothing. If pth norm will be you take power p and then take the sum, take 1 by power. So here there's the L1 norm, that is mod x1 minus y1 plus mod x2 minus y2 plus etc. mod xd minus y2. So that is the L1 distance. That is another distance. So the unit ball will be like this. See, the unit ball, the Euclidean thing is base. You look at the origin. So there it will be like this. That is 1 0 0 1. What is how one distance between 1 0 and half of L? So distance between no, it will be like this. I think wrong. Yeah. So if you look at the distance between 1 0 and 0 1 will be 2, but distance between 1 0 and half 1 0 half distance is again 1. So if you look at the unit ball, the counterpart in the L1 now, unit ball is all those things which are distance 1 from the origin. So distance 1 from the origin with respect to L1 now. So what is the distance of half to origin? 1. Distance of 1 0. So all these will be, this will be the unit ball. So I shouldn't say unit unit. There it's the unit circle. So this is the unit. It's not looking like circle, but
Actually,
you say unit ball. Okay. So I'm also used to, but some people say if you make the dimension 2, they say unit circle. I can say circle, but it doesn't look like circle. Huh? This I know I'm a bad artist, but this is definitely correct. I have got to call a unit circle. Circle in R2 with L1 norm. Yeah. So L1 norm is different from L2. L2 norm is the usual Euclidean. That is different. So this different norms are there. So Schoenberg's theorem is, so by general applying Schoenberg, we are not doing anything. Tree is embeddable isometrically in hypercube. Hypercube is embeddable isometrically in L1. This is easy. Yeah. So by Schoenberg's theorem, the distance matrix of a tree has one positive eigenvalue, n minus 1 negative eigenvalue. So one positive anyway, you know, by Perron theorem. So what is Perron's theorem?
Non-negative.
The distance matrix is non-negative, but you may need some irreducible or periodic things like that. They are all true because distance matrix is a connected graph, so every distance is positive. So it is definitely each non-diagonal entry in the distance matrix is positive. So by Perron theorem, one there is a positive eigenvalue and eigenvectors will all be positive. So there is one positive that you know anyway by Perron theory. That is the only positive. That is what they show in this, which is interesting. You cannot get any more positive. So Perron theory anyway will give you one positive. That easy. So this I don't need. So this Perron is only one positive. That's the only thing. That's all I wanted to say. So of course we can do something. We'll see. I will elaborate a little more on this. Maybe. And I want to do something about Steiner. I want to get Steiner distances. So once I get Steiner distance, there are some other interesting matrices which are associated with this. So I will do this. So this you want me to elaborate because Perron theorem everybody knows, or somebody doesn't know, you let me know, because I think it's known because I have seen enough. But for some people it may not be. You may not have known, and you think, okay, if I don't know, then I'm just not good enough. No. You are as good as anybody is. Yeah. You're going to do.
Yeah.
So those who don't know Perron's theorem, attend David's lecture. When? What is the time?
Tomorrow.
Tomorrow what time?
Evening.
Tomorrow evening. So I already used some Perron's theorem today, but proof is there tomorrow. I don't know proof is given to whatever. David will talk about it tomorrow. Yeah. Trailer. Yeah. So this is all. Yeah. Trailer, but yeah, come for the original. Yeah. So maybe we stop here.
Yes.
So this, how do we charge? I just want not to show them.
One quick announcement, as I was in the morning, that we would like to start by 9 AM so that we'll get enough space for the lunch. So 9 AM, I just confirmed, sir. 9 AM, that means you should be here by 9 AM. This one only concern is that you will not reach by 9 AM.
No, breakfast starts at 7:30. So
Yeah.
so have breakfast. We all of us will also have breakfast. We won't skip.
Correct. Yeah, bus will come at 8:45. Actually, it will leave from the place.
Food court.
Food court. Okay. I'll make sure that it starts by 8:45, so you are not late.
Yeah, maybe 8:30 first round, 8:45 second, something like that.
Last round is 8:45.
Last
Last round is 8:45. So before that, if you come, it is easy for us to actually start the lecture on time. So as you already would have right now, that starting time is very important for us. Ending time we don't mind.
I hope students say it's okay. I shouldn't say.
Ending time we don't mind. Please come on time so that it is easy for us everybody. Because we came here to learn something.
See, and if you have any comments, tell me. I find it too tough, too easy, whatever. You tell me, because I can factor it. Today is okay. Tomorrow, then almost half is done. Then after that, whether you tell me or not. So tell me now. Yeah. You can, if you're feeling, you tell David or Vinay. They will tell you. Anonymity will be guaranteed. So you don't have to worry about consequences. There is no consequence.
So thank you. We'll have tea and then we'll be back by 4:10 possibly.
Oh, okay, this is like, one.
ഈ വീഡിയോഗ്രാഫി മാത്രമേ ഉള്ളൂ വേറെ വീഡിയോഗ്രാഫി ഇനി ഫോട്ടോ എടുക്കാൻ
ಟೇಬಲ್ ಉಂಟಾ ಸ್ವಲ್ಪ ತೊಡಗ
ഇല്ല അതിന് നമുക്ക് അപ്പോഴും
In first 10 minutes, you sit and close, then later you stand at least so that you can check the video. Come and go for
teaching not comfortable.
Yeah, you have to find everything. That is there, will be comfortable.
No,
Could we just keep it there? No, no, it won't. There and there.
Thank you. Okay.
It's okay.
So, I will just discuss some of the basics of graph theory, but I would like to know what you already know, because I think you already know most of basic graph theory. So is there anything, can I know if anyone here is not acquainted with graph theory at all? Everyone knows. You are new to graph theory. Okay. You have not done any like single course also? So trees, etc. unknown. Okay, so I'll start from basics, but I'll also cover some of the slightly advanced topics which the speakers will require. So you've already seen examples of graphs. So we have um, graphs such as networks, sort of, that look like this. The basic objects being vertices and edges. Okay. So these dots which we draw in this way, or you can draw them in this way also. Okay, these are called vertices, and these
lines that join them. These are called edges. You don't have to draw them a straight line. You have curved lines also. So formally, if you want to define it, you say that a graph is an ordered pair G equals V comma E, where V is, according to one convention, a non-empty set, okay, called the vertex set, and E is a set of unordered pairs of distinct vertices. So the elements of the vertex set are called vertices. Okay, the elements are of vertex set are called vertices, and this E is a set of unordered pairs of distinct vertices. Okay, there are different definitions. You can take ordered pairs, or you can allow repetition of vertex. So I can also have an edge of the form V comma V also, but we are going with this unordered pair of distinct vertices because I think most cases you will be discussing what are called undirected simple graphs. So this is specifically a simple undirected graph or undirected simple graph. Undirected and simple. Okay, so edges do not have directions like this, and we do not allow self loops, edges joining vertex to itself, nor also do we allow two different edges between the same pair of vertices. Okay, so this would be called, if this was there, it will be called parallel or multiple edges, and this would be called a loop or self loop. So we don't allow this, so that's why it is simple graph. Okay, so this definition will do, the definition I gave will do for undirected simple graph. So usually we say that whatever is the number of vertices, the number of vertices is the order. Okay, number of edges is the size, but I think for the most part I'll not use these terminologies. Okay, so then let's look at some examples of graphs. Okay, one graph with, let's say, 5 vertices and 7 edges. Okay, there are 5 vertices here. We can label them as 1, 2, 3, 4, 5, or V1, V2, V3, V4, V5, and so on. Okay, the edges you can label as E, F, G, or E1, E2, and so on. But we can also just refer to them by the labels of the vertices that they join, which are called the end vertices of the edge. So this edge is 1, 2. Okay, we'll just call it as 1, 2 normally. If we need, we'll name it, but otherwise we can just say 1, 2, 1, 5. 1, 2 is the same as 2, 1 because we're considering unordered pairs. So I will write edges in this form, UV. Okay, you can also write U comma V or U comma V like this, but I will use this notation if necessary. Okay, another graph is this. Okay, this one is another graph, say H. Now there is some difference between G and H. Right? If you consider this graph G, this one. Oh. So if you consider this graph G and this graph H, there is some very glaring difference between them. Can you say what it is? Yeah, G is connected in some sense and H is disconnected, right? So if you want to formally define connected and disconnected, we need some other simpler notions to be defined. Of course, if you study topology, you have all studied topology. There you have some notion of connectedness. Two different notions of connectedness you have studied. One is just connectedness in terms of separating set and all that. Another is path connectedness. Path connected means between every 2 points, there is a path joining, which is completely inside the space. So it's called path connected. So in graph theory, we have that notion only. Connected means path connected. So for that, we need to define what is a path. Okay. So it's quite simple. So if you consider G now, for example, I can consider this. I can go from 1 to 5, then 5 to 2, 3 to 2 to 3, 3 to 5, 5 to 4, right? So I can consider that as walking on the graph. So that's called a walk. So walk in a graph or on a graph is just, so here what is it? What information is there? If we want to encode this walk as a piece of information, what information is actually required? I don't have to draw the whole graph and then draw the walk on it, right? I can just, if I have the graph already, I can just encode it in minimal manner. How? Alternating sequence of vertices and edges. That's one definition. So I can say I don't remember the original work. Let's say 1, then 1, 5, 8, then 5 to the vertex 5, then the edge 5, 2, then the vertex 2, then the edge 2, 3, and so on. So if I write this, it looks like this. Okay, and change this. So vertex 1, followed by, in the sequence, I'm taking the edge 1, 5. Okay, I'll write it like this. So I'm starting with vertex 1, then taking the edge 1, 5 to go to vertex 5, and then taking the edge 5, 2, which is same as 2, 5, to go to vertex 2, right? And then taking the edge 2, 3 to go to vertex 3, and so on. But because we are discussing simple graphs, some of this information is redundant. Correct. We don't need to specify the edges, because if I say I'm going from edge vertex 1 to vertex 5, there is only one way of going that from 1 to 5, that is the edge 1, 5. Because there are no multiple edges, I do not need to specify every edge. So in case of simple graphs, the definition is also simple. Just it's a sequence of vertices. With what constraint? That the successive terms in the sequence are adjacent vertices of the graph. So walk, if I write it formally, you say sequence of vertices. I'll use notation to make it clearer. Okay, V1, V2, etc., Vk, where each Vi is adjacent to Vi plus 1 for every I from 1 to k minus 1. So V1 is adjacent to V2, V2 is adjacent to V3, and so on. Vk minus 1 is adjacent to Vk. So this adjacent word I have not used before, but I think you know it. If there is an edge joining two vertices, then we say that U and V, those two vertices, are adjacent. Okay. Otherwise, they are non-adjacent or not adjacent. Okay. I might use this notation also, U tilde V, for adjacency. Okay, so a walk is a sequence of vertices of the form V1, V2, etc., Vk, such that each Vi is adjacent to its next successor, Vi plus 1, of course, and its predecessor also. Then a path is a walk in which the vertices are not repeated. Okay. So when considered as a sequence, all the terms in the sequence are distinct. Okay. So the earlier example I gave is not a path. It's a walk, but not a path. So I think I did 1, 5, 2, 3, 5, 4. So this is not a path because 5 is repeated in the sequence, right? But it's a walk. Whereas if I do 1, 5, 2, 3, 4, that is a path. So, yeah. In some other terminology, this walk is called a path, and this path is called a simple path. So that simple path terminology agrees with the usual geometry definition of simple path, which is non-self-intersecting, right? But I'll use this. Okay. Usually, most graph theories use this terminology. Okay, so this is a path. So now we can define what a connected graph is. So a graph G is connected if, okay, so again, something terminology that I did mention. Specifically, we say that this walk, right? Specifically, we say that this is a walk from V1 to Vk, or between V1 and Vk, or joining V1 and Vk. Same thing for path. So G is connected if between, or let's say, every two vertices of G have a path between them, or are joined by a path. Okay. Every two vertices are joined by a path. That includes a vertex in itself, but that's always true because a vertex in itself that's an empty path. If you just write one vertex, consider that as an empty path. So that's always considered as a path. Okay. You don't have to say distinct vertices. So in this case, clearly G is connected, whereas this second example H is not connected because, for example, if I take this as vertex 1 and this is 2, there is no path from 1 to 2. There is no path from 1 to anything else here either. This, neither this nor this, right? Okay. So when it is disconnected, again we can see that although H is disconnected, it has something like two parts in some sense, correct? If I ask you how many parts are there in H, even if you're not studying graph theory before, you would intuitively say that there seem to be two pieces or two parts. So then the question is, how do we define this as one part? How do I say this is one part and this is another part? So again, this is only a matter of formally defining what we intuitively recognize. Okay, so for that, first of all, we need to define the notion of a subgraph. Okay, any field of mathematics you study, higher mathematics that you studied, any kind of algebraic or combinatorial structures you studied, you know the notion of substructure for a structure. Okay, subgroup, subspace, etc., subset. So here also we want to define a subgraph. The obvious definition is that it's some smaller part which is itself a graph. Okay, like subgroup is some subset which forms a group. Okay, but under some conditions, right? Under the same operation in that case. So here we want to say that, for example, again, if I take this graph G, suppose I take vertex 1, vertex 2, vertex 3 along with this edge 1, 2. That is a subgraph. So for example, I take this 1, 2, and 3. Okay. This forms a subgraph of G as an example. So if you want to formally define it, what is sub in this? The vertices as well as the edges. Okay. So any graph edge is a subgraph of a given graph G. Okay, I think need to be careful with this. A graph H is a subgraph of graph G. If so, recall the notation. The graph is an ordered pair of the form V, E, where V is a vertex set and E is the edge set. So conversely, if I am already given a graph G, if I'm already talking about a graph G, then I will use this notation V of G. and E of G to denote the vertex set and edge set of the graph. Okay, again, this is some standard notation. So this is just as a function. Given the graph, V of G gives me the vertex set, E of G gives me the edge set. With that notation here, a graph H is a subgraph of graph G if the vertex set of H happens to be a subset of the vertex set of G, and the edge set of H happens to be a subset of the edge set of G. Any questions on this? Okay. Is it true that given a graph G, if I take some subset of the vertex set and some subset of the edge set, that will form a subgraph? Not necessary. Correct? So that's why we start with a graph H that satisfies this will be called a subgraph. But if I just take an arbitrary pair of subset of vertex set and subset of edge set, that may not be a graph at all. Because to be a graph, what is this? You need a non-empty set V. And E should be a set of unordered pairs of distinct vertices, right? Distinct elements of V. So that condition may not be satisfied if I take arbitrary pair of subsets, right? So for example, yeah, suppose I take say V primes, V is the original 1, 2, 3, 4, 5, 6, and E is the original edge set. Suppose I take like V prime is equal to 1, 2, 3. E prime is equal to 1 to say 1, 4. This is not going to work because this E prime cannot be the edge set of any graph with this vertex set. Correct. So just to be careful, okay? You can't take, so for example, this comes up if you're trying to enumerate all subgraphs. So suppose you're writing an algorithm to find, brute force algorithm to find all subgraphs. So if you just take all possible subsets of vertex set and all possible subsets of edge set and pair them up, you don't get all subgraphs. So that's where you need to be careful. Otherwise, when you're looking at it in drawing, obviously you won't make this mistake. Okay, so subgraph notion is understood, I hope. Then, yeah, if the need arises, I'll introduce spanning subgraph, into subgraph, etc. Probably we won't need it. So we go back to this problem. We want, now that we have defined notion of connected graph, and whatever graph is not connected, we call it disconnected. When we have a disconnected graph, we seem to have this sort of different number of pieces or parts of the graph, which we want to formally define. Okay. So obviously the part or piece or what is going to be called a component of a graph, that is a subgraph. But is every subgraph such a component? Do we want to say that any arbitrary subgraph is a component of the graph in this sense? When we say there are two parts here, you want to say there are two parts, not five, right? For this, you don't want to say there are 5 parts. So we want to define it so that this becomes one component, but this does not become a component. And of course, if I take this also should not be one component because that's not connected anymore, right? So we want to define connected components or what simply we call components. How do we define it? It should be connected first of all, but every connected subgraph is not a component. So for example, if I take this is not, right? But this is. So it should be maximal with respect to the property of being connected, right? So putting it in brackets because usually we just say component, but although the full name is connected component. Okay, connected component of a graph G is a maximal connected subgraph of G. Any maximal connected subgraph of G is a connected component. So again, I'll expand this example with some more components. Okay, how many components are there? Yes. 5 or 4? 5. So that 13, 14, 15, 16 is not one component, obviously, right? Because although drawn it that way, the edges are crossing, but they're not actually, there is no actual path, right? You can't say 13, 16, there is a path because this is not a vertex at all. Right? Okay, so the components are 1, 2, 3, 4, 5, 6 and all those edges, 7, 8, 9 and all those edges, 10, 11, 12, all those edges, 13, 15 and 14, 16. Okay. So let's see why this definition works. Suppose I try to say this one, right? Suppose I try to say that this one, 13, 14, 15, 16. Suppose I try to say that this is a component. How would you say by this definition that it's not? It's not connected, right? There is no path from 13 to 16. So that way it's ruled out. Okay. Suppose I try to say that, intuitively we already know this. So suppose I try to say that 7, 8 is a component. This also you want to say it's not. How will you say that this does not satisfy the definition? It is not a maximal connected subgraph. So when you say maximal, it is always with respect to some property. There is no such thing as maximal parent of anything else, right? So it's maximal as what? As a connected subgraph. That means what specifically more formally, or if you expand the definition, what does it mean? It is a connected subgraph and induced is true, but this is also inducible. 7, 8 is also inducible. So that's not it.
You could add those vertices and they get right.
Yeah, you cannot have any larger subgraph in the sense if you okay. So how do you define proper subgraph? Is easy to define. It's a subgraph whose vertex set or its set or both happens to be proper subset, right? Whichever. Okay. So that is proper subgraph. So proper subobject we can always define for any mathematical object. Okay, so if you want to say maximal connected subgraph, it is a connected subgraph which is not the proper subgraph of any other connected subgraph, which is not proper subgraph of any connected subgraph. Correct. It is its own subgraph, but not a proper subgraph. So it's right. So it's not the proper it is not the proper subgraph of any connected subgraph of G. Correct. So here, if I just take 7, 8, then you can say here is another graph 7, 8, 9, which is a connected subgraph of G. But 7, 8, that one I took, happens to be a proper subgraph of this larger subgraph. And therefore, the original 7, 8 is not a maximal subgraph like that. Okay. So why not only vertices? Because suppose I take 10, 11, 12. I can't just talk about vertices. If I take 10, 11, 12, is this a component this way, right? And the edge is 10, 11, 11, 12. Is this a component? No, because all the vertices possible are there. If I add any more vertex, it will be forced to be disconnected. But I have not taken this edge 10, 12, which is originally there. So that way it is not maximal, right? If I don't take 10, 12 also, it is not maximal. So that's why both vertex set and edge set, I mean, if either one of them is a proper subset, it is a proper subgraph. And therefore, in this case, it is not a maximal connected subgraph. So in general, you can define maximality with respect to any property, right? So maximal subgraph with respect to some property. Similarly, minimal subgraph. So it should not properly contain any other subgraph with that property, means it is minimal with respect to that property. For connectedness, we don't want to define minimal because it will always end up being single vertex, right? Similarly, for other properties, we'll define minimal but not maximal because maximal will end up being the whole graph. Okay. Okay, fine. Now before moving further, we'll go to the definition of adjacency matrix and adjacency matrix for now. Okay, because we want to also see how to encode these graphs efficiently. There are different encodings. So if you want to represent it in a or encode it in a computer, in a programming language, for example, there are different representations. One very efficient representation is adjacency list. In terms of storage, that is very efficient because very briefly I'll tell you, but I don't think we need it, so I'll not formally define it. For example, here I can see that if I start with 1, I can just say 1 is adjacent to which other vertices? 1 is adjacent to 2 and 4 and 6. So I'll just store it as a list saying 1 is adjacent to 2, 4, 6, 2 is adjacent to 1 and 3, 3 is adjacent to 2 and 4 and so on. So just that list. Okay, that much only. It is efficient for storage, but for computing it's not very efficient because if I want to check whether some arbitrary thing is adjacent or not, I have to go to that and check in that list. Okay, so that's not very efficient. Depending on how you store it, especially if you store it as a list. And if you know some computation complexity there, basic complexity there, to access a list, okay, it's not an array. You know the difference between array and list in terms of computation complexity? You all know arrays, basic programming. Okay, if you don't know, it's fine. There are some algorithms to discuss, that's why I'm discussing this. So an array is a data structure where okay, that is the difference between mutable and immutable array. But suppose you cannot change something about the array though. What is it? At least in the basic definition, you cannot change something. It is not the value, it is the size of the array. Okay, because the basic feature of array, what defines an array is it is constant time random access. That means if I want to access the ith element, it takes only one operation to do that. Whereas when we call it a list, right, like in Python lists, the difference is if I want to access the ith element, it takes O of I time. That means I have to start from the first and always trace back. You may not write it that way. The programming language may have a function which directly gives you it, but what goes on in the background it is that it always starts from the first and goes until it finds that. Okay, it goes until it counts to I and then finds. So it's like you have a stack stack of papers and you have to count and find it. There is no, you're not labeled it so that you can say, this is the 10th one. You have to count and find 10. That is the difference between array and list. Okay. So there are different reasons why these different data structures are used in for particular applications. One is more efficient for some applications, one is efficient for the other. Okay, so if you're going into algorithmic graph theory, you need to understand this. Otherwise, it's fine. So another way of representing a graph is using a matrix, because another way to think about the graph is you have the set of vertices, and instead of thinking of these as edges, what you have is simply what? Another mathematical object that you already studied even in school level, you studied this. 1 and 2 are adjacent, 1 and 3 are not adjacent, and so on, right? So what is that? Yes. Exist or doesn't exist. So yeah, you are going to the other one, which I was not thinking of. That is Boolean, this one, true or false. Yeah. Yet another way to think of it is it's simply a relation. It's just a relation between vertices. You can call it edges, but simply it is saying, are they adjacent or not? Because we are not taking directions. Even if you're taking directions, you can still think of it as a relation. Yeah, but here it's very simply a symmetric irreflexive relation, let's say, because no vertex is considered adjacent to itself. But if U is adjacent to V is adjacent to U. So it's simply a symmetric relation, symmetric irreflexive relation. Okay. And yeah, using Boolean values, you can encode this relation as for every pair. So for this graph, again, in this example, smaller graph. Okay. So what I can do is, so you already saw distance matrix, so it's nothing new. Here, I'm just going to write 0 or 1. according to whether I and J are adjacent or not. Okay. Well, non-adjacent or not, respectively. So 1 is not adjacent to itself, so 0. 1 is adjacent to 2, so 1. 1 is adjacent to 3, no. 1 is adjacent to 4, no. 1 is adjacent to 5, yes. Okay. Then, yeah, we already noted this is a symmetric relation, right? So if 1 is adjacent to 2, 2 is also adjacent to 1. So what is the definition formally that I call this A? Then Aij is equal to 1 if I and J are adjacent. So I'm using the tilde notation. 0 if they are not adjacent. 0 otherwise. Okay. The Ij entry is 1 if Vi and Vj, if you want, you can call it. Here I've labeled 1, 2, 3, 4. So I'll just say Ij. Okay. I and J are adjacent. 0 otherwise. Okay. So obviously, if Aij is 1, Aji is also 1. If and only. Correct. So once I get a row, I also get the column immediately. It's similar to what you did for distance matrix. So I can just fill this in by copying this. And another thing is, what can I say about the diagonal entries? They are all 0. Again, that's the same in distance matrix, but there it is because distance from a vertex to itself is 0. Here it is because no vertex is adjacent to itself. Then 2 and 3 are adjacent. 2 and 4 are non-adjacent. 2 and 5 are adjacent. Okay. So again, that 1, 0, 1 I can copy down as a column. Then 3 and 4 are adjacent. Okay, I'll copy immediately. 3 and 5 are adjacent. Yes. 4 and 5 are adjacent. Okay. This is the adjacency matrix. Formal definition is this. It is. Sometimes you also write it as a function like A or G. So even if I have a different graph H, then I can say something like A2 or AH is equal to A of H and so on. So just convenience. It's a vertex, I'm sorry, it's a matrix whose rows and columns are indexed by rows and columns are indexed by, I'll just say V of G. Actually, the vertices of G taken in some order. You have to force some order here because you have 1, 2, 3, etc. rows, right? The rows are not unordered. So you have to force some order there. So you take them in some order, but I'll just write it as a set only. Indexed by V of G with the Ij entry given by this, where I and J denote the ith and jth vertices. Just take them as ith and jth vertices. Now, if I change the labeling, how will the matrix change? So that came up in for distance matrix also it came up. So if I change the labeling of vertices, that means if I reorder, the actual labels don't matter. The matrix does not represent the value of the label at all, right? So I can call it ABCD also, that doesn't matter. But if I change the ordering of the labels, so I'll just say relabeling, how does the matrix change? Let's take a simple example and see. Okay. So we'll take let's say this one. And with this ordering, 1, 2, 3, 4, usual ordering, what is the matrix? 0, 1 is adjacent to only 2, right? 2 is adjacent to both 3 and 4. That's it. Okay. If I change it so that it's, let's say, suppose this is the ordering, new ordering. Okay. Now, 1 is adjacent to only 4. Right. 2 is adjacent to 4 only. Right. So 3 is adjacent to only 4. Is that right? Yeah. Every vertex 1, 2, 3 are all adjacent to 4. 4 is adjacent to 1, 2, 3. No other adjacencies. So that's it. Correct. How are these matrices related? How can you get one from the other? Multiplication by permutation means basically if you reorder the rows and columns, right? But simultaneously. That means, so obviously this, see, if you look at the graph, we are not formally defined isomorphism of graphs. But if you look at the graphs, clearly you can map the first graph to the second graph in this manner, preserving the structure. I can map 1 to 1, right? 3 to 2. I can even map 3 to 3 also, but let's try this. 3 to 3, 3 to 2, 2 to 4. That is inescapable. There is no other possible mapping. Why? Because in the first graph, 2 is adjacent to 3 different vertices, and no other vertex has this property. In the second graph, 4 is adjacent to 3 different vertices. No other vertex has this property. So if I'm trying to see this graph as a relabeling of the first graph, I am forced to acknowledge that 4 is the relabeled vertex 2. Correct. There is no other. But the other vertices are actually interchangeable. But let's take it in the order that we see it. The geometric representation of the graph doesn't matter. Right. I can draw it in different ways, but this is easy to see. Okay. So, for example, this 2 has become 4 means this second column, for example, has to become the fourth column. At least that's what we think first. But if you look at the second column and fourth column, they are not exactly same. Second column is 1, 0, 1. Fourth column is 1, 1, 1, 0. Why? Because the row is also representing the vertex. The vertex is represented by row and column, right? So second row also has to become fourth row. So to go from first matrix to second matrix, you have to basically do something like R2 and R4 are interchanged. At the same time, C2 and C4 are interchanged. Okay, then some other reordering of the others. So that means simultaneously you have to permute the rows and columns. So to simultaneously permute rows and columns, you need to multiply by, to permute the rows, you need to multiply by a matrix, a permutation matrix on the left, and to permute the columns, in the same way to permute the columns, transpose of the permutation matrix on the right. Okay. So of course, you know that permutation matrices are orthogonal. So P transpose is in fact P inverse. Okay. P transpose is I. So if I call this A prime, not bad notation, because sometimes some people use transpose for that. So I don't want to call it B either. I'll call it A2. Okay. First one is, let's say, A1. So this A2, this is A1, this is A2. Then A2 is equal to PA1 P transpose for some permutation matrix P. We can actually figure out the permutation without much difficulty if you write down the permutation and then permute the identity matrix according to the same thing we are doing. We get that permutation matrix, but we don't have to do it here. So that also tells us that these two matrices are similar. They are similar matrices because of this. Okay, because P transpose is I. P transpose is in fact P inverse only. Okay. So this tells us some other things that, for example, when you define what are called the eigenvalues of the graph, which is nothing but the eigenvalues of the adjacency matrix or the adjacency spectrum. The adjacency spectrum is independent of labeling. So normally, how you define it is, you say that you take the graph, take its adjacency matrix, find its eigenvalues. Okay. Huh? Is it fine now? Yeah. Hopefully. Okay, so if you take the adjacency spectrum, which is taken as which is obtained by taking the adjacency matrix and its spectrum, the first question is it depending only on the graph or also on the particular labeling of the graph or ordering of vertices? So this shows you this relation between the adjacency matrix before and after relabeling. That shows you that the adjacency spectrum is invariant of the ordering of the vertices or labeling of the vertices. Okay. The same thing holds for the other matrices that we define, like Laplacian matrix and distance matrix, because relabeling is just permutation, simultaneous row column permutation. Okay, so that's one thing. Now we want to see what other information is encoded in this adjacency matrix easily. Of course, it encodes the complete information about the graph. If I give you the adjacency matrix, you can completely reconstruct the graph. But what are the pieces of information that you can get more simply without actually drawing the graph? Can you infer anything from the adjacency matrix about the graph parameters? So I need to introduce some more graph parameters. I already told you about the order and size. So the order is obvious. The order of the matrix in the usual sense is nothing but the order of the graph. The number of rows or number of columns which are equal is the number of vertices by definition, right? Because we are indexing the rows and columns by the vertex set. How to get the number of edges? Okay, one way is you can count the number of ones above the diagonal, for example, or below the diagonal, your choice, same. To count the number of ones above the diagonal or below the diagonal, that is going to be the number of edges, because for every pair ij where there is an edge, ij entry will be 1. And you don't have to, if ij entry is 1, ji entry is also 1. So you take the convention that you're taking only I, let's say I less than j only. Okay, and counting those, because I equal to j anyway won't arise, no self loops, right? So that's one way. Another simple observation here is, okay, let me introduce another notation, a notion rather, that of the degree of vertex. So again, in this, let's say in this graph, 1 is adjacent to how many vertices? 2 vertices, whereas 5 is adjacent to 4 vertices and 2 is adjacent to 3 vertices. So this simple parameter is called the degree of a vertex. So which we denote as DEG of V with bracket or without bracket. Again, we want to specify the graph means you can say DEGG of V equal to number of adjacent to V. Okay. These vertices adjacent to V are also called neighbors of V, in case anyone uses number of neighbors of V. Okay. In a multi-graph, this definition is a bit different. You say number of edges incident with the vertex, whereas where the edge E is incident with the vertex V if E is the pair UV. Okay. So there you also count it. So for example, if you have this vertex as degree 3, not 2, although it's adjacent to 2 vertices, its degree is 3. But we don't want that, so I'll just use a simple definition. So here, going back to this graph, let me write down the degrees here. This is of degree 2. This is of degree 3. This is of degree 3 as well. This is of degree 2. This is of degree 4. Okay. Can you get this information by looking at the adjacency matrix without reconstructing the graph? Yes, because if you take the ith row, which j entries will be 1? Whichever j are adjacent to I. So that means the number of ones that occur in the row will be equal to number of vertices adjacent to Vi, the ith vertex. So if I just take, for example, second row, it has 3 ones. That means degree is 3. Whereas first row, 2 ones. That means degree is 2. So it is, in other words, a row sum. If I take the row sums, it is giving me exactly that, right? The degrees. 2, 3, 3, 2, 4. That is what I have here also. 2, 3, 3, 2, 4. Right? So it is a row sums or column sums. Equivalently, it is a column sums. Okay. Algebraically, how do I write this? Matrix algebraically. How do I get the row sums? If I have the matrix A, what is the algebraic way of matrix algebra way of getting the rows without seeing sum of the rows, sum of the row entries and so on? Multiplying by E1 will give me first column, E2 will give me second column, and so on. So what is
Multiplying
J? Which J? All one's vector. Okay. So I multiply on the right by the all one's vector, and just call it 1n. Okay. All one's vector of n components. This is going to be, yeah, degree 1, degree 2, and so on. Okay, it is going to be the vector of degrees. In general, you know, if you multiply any matrix on the left by, I'll call this also 1n transpose, or convention that column vectors are usual vectors. So this is going to give me same thing here, but in general, for any matrix A, this is going to give me the column sums, and multiplying on the right will give me the row sums. So if I multiply both on the left and right at the same time, sum of all entries. Okay. We already made an observation here that if you take the entries above the diagonal or below the diagonal and count the number of ones, that gives me the number of edges. If you add all the entries of the matrix, then what do you get?
Twice the number of edges.
Twice the number of edges, because whenever there is an edge ij entry and ji entry will be 1. And this is a special matrix. It's a 0, 1 matrix. So adding is the same as counting. Means counting ones, right? If I add a number of ones and zeros, that is the same as counting the number of ones that occur as terms. So if I do 1 transpose A1, this gives me, whichever way you do the apply the associativity, right? Whichever way you multiply, it gives me first the row sums and then the column sum, but first the column sums and then the sum of those entries. So it gives me the sum of all entries. Okay. And obviously this is equal to twice the number of edges. Whereas if I read it like this, 1 transpose into A1. A1 means what? The vector of degrees. So if I do this, then again this is a matrix. So if I do 1 transpose times that, this is going to be sum of all degrees. Correct? That's right. Simply summation over V, degree of V. So there are two ways of interpreting this, gives me the two answers. So obviously these must be equal. This is the familiar handshaking lemma or degree sum formula, right? Yeah, of course, you can get it directly by looking at the graph. It's just a combinatorial result, okay? But this is a basic result that the sum of all degrees of a graph is going to be the twice the number of edges. Number of edges is half of the sum of the degrees. And this also has a corollary that number of vertices with odd degree in any graph must be even. There must be an even number of vertices. Okay, okay, you can try that exercise if you haven't seen it. Now let's see what other information is there. Let's take another graph. Okay. Okay, let's see. I'm not sure whether it's illustrative enough as an example, but let's see. So what is the adjacency matrix here? 1 is adjacent to 2 and 4. 2 is adjacent to 3 and 5. Oh, I think it's 4. Is adjacent to 5. 4 is also adjacent to 5. Okay, can we find a square? So 0, 1, 0, 1, 0. That means 0, 1, 0, 2. Oh, by row, that's easier. 1, 0, 1, 0, 1. So that means first 3 rows. I mean, alternate rows. 2. Okay. 0, 1, 0, 1. So second and fifth rows, correct? Third row is going to be the sum of the second and fifth rows. So 1, 1, 2, 1, 1. Please correct it if it's not correct. Okay, 1, 1, 2, 1, 1. Fourth one is first and last row. So 0, 2, 1, 2, 0. No, no. So I did correctly. Is it symmetric so far? Okay, then I can just complete it. Last one is going to be 3. Is that right?
Fourth element. Fourth row, fourth element.
4 element. Yeah. 4 element cannot be 1. It should be 2, right? 2, 3, 2, 3. Okay. 2, 3, 2, 2, 3. Yeah, looks fine. At least diagonal elements are correct. Okay. Okay, fine. Can you yes, can you mistake? No. Can you interpret the diagonal entries? At least guess. Anyone who's not seen the result before. Can you look and guess by the numbers what they are? 2, 3, 2, 2, 3. Okay. They are the degrees. Fine. Right. Okay, I want the non-diagonal entries as well. So 1, 2 entry is 0. Whereas 1, 3 entry is 1. Now if you look at this, 1, 2 is an edge. 1 and 2 are adjacent. 1 and 3 are not adjacent. But here 1, 2 entry is 0 and 1, 3 entry is 1. But it's not just that, because for example 1, 5 entry is 2, not 1 also. Right? Again 1, 4 entry is 0. But they are adjacent. And 1, 5 entry is non-zero, but not just non-zero, it's 2. Okay, so how to interpret this? So, yeah. Yeah, so if you see it before you know it, let's try to find out if you have not seen it or forget what you know. Let's see. So, in general, what is the ij entry of the product AB in index notation? AIK BKJ and sum over the repeated entry, right? Summation convention, or you can specifically write K equals. So I'll just consider n by n matrices. You can write this in general for rectangular, but let's not worry about the dimensions exactly. So everything is 1 to 1. Okay. You can generalize it obviously. So in index notation, it is simply going to be Aik, Bkj, sum over k. So in this particular case, what I want is A square. So A square Ij means summation k equals 1 to n Aik, Akj. Can even write this as Ajk because it's symmetric, but that doesn't matter. Aik, Akj. Now here again, what is peculiar is this matrix A, not the A square, A is a 0, 1 matrix, correct? So being a 0, 1 matrix, each term here has only some possible, what are they? 0 and 1. Okay. So this is always 0 or 1. Not only that, when is it 1?
Common entries.
Like, no, in terms of a product, if I write the product of two numbers, P and Q, if P and Q are both 0 and 1, when is PQ equal to 1? If both are 1. So the only possibility for the term to be 1 is if, so 1 if and only if Aik equals Akj equals, sorry, thinking of the other case. Yeah, equal to 1, otherwise 0, right? Otherwise means either Aik or Akj or both will be 0. Okay. Not only that, if the entry is 1, then in the total summation, I'm going to get like 0 plus 0 plus 1 plus 0 plus 1, etc. So on, right? So in this, the summation is just going to be the number of ones. Again, we observed that earlier. Sum of zeros and ones is simply counting the number of ones. Summation and counting are same. Okay. So I'm just counting the number of terms equal to 1. But which are the terms equal to 1? Those terms in which Aik and Akj are both equal to 1. Aik and Akj are both 1 in terms of the graph. What does that mean? Aik is 1 means Vi and Vk are adjacent. Vi is adjacent to Vk. Akj is 1 means Vk and Vj are adjacent as well. Okay. Now the summation is over what? K. So I and j are fixed. So this k varies over different vertices, but the only ones that count are the ones that are adjacent to both Va and Vj. So this summation is just counting the number of common neighbors of Vi and Vj, which vertices are adjacent to both Vi and Vj. Another way to say this in terms of path, what you said earlier, or in walks, what is it? Number of walks of length 2 from Vi to Vj. So length of a walk we didn't define earlier, but again the simple definition is if you have the sequence, then this is a walk specifically of length k minus 1, k not k. The number of steps that you take. If you are just at V1, you're not taken any step, it is 0. 1 more means 1 step, 2, and so on. When you reach k, you taken k minus 1 step. So, right. So length k minus 1. So this is number of walks of length 2. I mean, why do we say it that way? Because if you take a cube, what is going to happen? A cube ij is again summation, double summation. Okay, maybe we'll write that explicitly. Both from 1 to n. Aik, Akl, Akj. Okay, in general for ABC, any matrix ABC, Aik, Bkl, Alj, sorry, Clj, right? In this case, Alj. Yes. So again, you analyze this and say that this can only be 0 and 1, and it's 1 if and only if all 3 entries are 1. All 3 entries are 1 means Vi is adjacent to Vk, and Vk is adjacent to Vl, and that Vl is adjacent to Vj further, right? I and j are fixed. So you have all these. Okay. So all the walks of this kind, walks of length 3 in this case. So in general, if you take a power n ij, that is going to be, so this is going to be number of walks of length 3. And so Aij, A power n ij is going to be number of walks of length n. Maybe I should not use n because usually I use n for order. So not yes. Number of walks of length k. Okay. So you get that information is in adjacency matrix. So another thing we observed is the degrees, the diagonal entries are the degrees. Why is that true? Do we need separate analysis for that? What is a walk of length 2? This is true for all ij. I didn't assume that I and j are distinct. So what is a walk of length 2 from vi to vi? You have to go to some neighbor and then come back in the next step. Because only 2 steps are there, walk of length 2. So you have to go to some neighbor and come back. If you go to some other vertex, it is a neighbor only. If you come back, that's one more step. So this every walk of length 2 from vi to vi is going to some neighbor and coming back, and every such walk of length 2 counts a unique neighbor. So the ii entry is nothing but the number of neighbors, which is the degree. What will you get if you take ii entry of a cube? A cube ii entry will do. ii entry, not the okay, ii entry. Yes, number of. So literally it is the number of walks of length 3 from I to itself. What does that look like? So if you go from Vi to some Vj and to some Vk and then come back. So if you are going, you have to go to a neighbor, then from there something else, then that thing has to be a neighbor of Vi, otherwise you can't come back in one step. You have to come back in one step, right? So this has to be a neighbor as well. But that means this is a triangle, what is called a triangle. If you're not familiar with the terminology in graphs, it's called a triangle or complete subgraph of order. Okay. So if you just call this structure a triangle, as a subgraph, it is a triangle, but actually you are enumerating it as a walk of length 3, right? So if you have one such triangle, then how many such walks do you have? 2 for the same triangle. Okay. See, the summation is not counting the subgraphs, it is counting walks. But the same subgraph is giving you 2 different ones. So if you take this graph, just the triangle graph itself, vertices 1, 2, 3, and if you take a cube, I know that its first diagonal entry is going to be 2. Okay, I don't have to write a to begin with. I know that the 1, 1 entry is going to be 2 because there is one triangle like this, but you can traverse it in 2 different directions, either this, okay, or this, right? So that entry is going to be 2. Okay, same thing for the others. Now, of course, the other entries you can write by counting number of walks of length 3 and so on. Okay. So next question is, obviously, if you take the trace of a square, it's going to be summation of all the degrees, which is, as we have seen, twice the number of edges. Here, what do I get? If I take trace of a cube, what do I get? Is it twice the number of triangles? Why is it twice the number of edges there? I mean, we know one proves that matrix proof, but simply why is it? Because every edge is incident with 2, every edge has 2 end vertices. So the same edge is counted by 2 different ii entries, correct? Here the same triangle is counted by how many different ii entries? 3, because it is in 3. But each term counts it how many times? 2 times. Each triangle is counted 2 times by each of its end vertices, and it has 3. So it is counted 6 times. So this is 6 times the number of triangles in G. Okay. So for this you will get just 6 because 2, 2, 2. But in general, if you want to count number of triangles, take a cube, take the trace. Okay, that's one way, right? So as an exercise, you can try trace of a power 4, or no, not trace of a power 4. What is the number of C4s, okay, or cycles of length 4? This is called a cycle of length 4. How do you get the number of cycles of length 4 from the trace? But you can't just get it from the, I mean, not just from a power 4, you need some other information as well. You need the information about degrees and so on. Okay. It's not that simple, because a walk of length 4 is not just this, there are other possibilities. So that's a more complicated formula. It's a good exercise. Okay, I'll briefly discuss line graphs because again, I think they need it. So it's not just it's not really a proper continuous graph theory talk. It's just a bunch of topics that you will need as prerequisites. So line is another name for edge. Harari, if you read, he uses points and lines rather than vertices and edges. So this line graph, we don't call it edge graph, but line here stands for edge. So say sure, this graph. But I label the edges now. So we define adjacency of vertices, but obviously you can also define adjacency of edges. So you say that edge EI and edge EJ are adjacent if they have a vertex in common. Okay. In a simple graph, they cannot have more than one vertex in common, right? Because two vertices are common, that means they are parallel edges, which is not allowed in simple graph. So they are adjacent if they have a common end vertex. So EI looks like this and EJ looks like this, whatever the labels are. Okay. So now, because we have this notion of adjacency of edges as well as vertices, it's natural to ask, can we define some new graph in terms of this? Yeah, we just consider the edges as vertices of a new graph. Same names you're using, but don't think of them as edges, think of them as vertices. How many? More. We'll add one more edge because should not think that number of edges here is related to, I mean, number of vertices here is related to number of original vertices. Originally you have, let's say this is also that. Okay, E6. Okay. Okay. So the obvious definition is in the new graph, you make the vertices EI and EJ adjacent if and only if the edges EI and EJ are adjacent in the original graph. So here E1 is adjacent to E2 and E3, and that's it. Yes. Then E2 is adjacent additionally to E3 as well as E5 and also E4. Correct. E3 is adjacent additionally to E4. Yeah. E5 is adjacent to E6. E4 is adjacent to E6 as well. Is that? Yes. Any more? Sorry. Oh yeah, E1 and E5 are adjacent. Sorry. Okay. Yeah. So this is the line graph of, if this is G, this is the line graph of G. Okay. Simple definition, simple to understand. There are some characterizations of line graphs in the sense that you can ask, Take an arbitrary graph. Can this graph, so the converse question, or the reverse question, can this graph be the line graph of some other graph? So not every graph is the line graph of some other graph. So the simplest example is, you know it, a line graph which is not the line graph of any other graph. Yeah, K13. It's a star, so I'm not defining star and all that. But yeah, this graph is not the line graph of any graph. Okay, whatever graph you take, it's not the line graph. You can prove that without much difficulty. You can just take that, suppose it is. I'll call this E0, okay, central vertex. I'll call it E0. Suppose it is the line graph. Then you know that the original graph has four edges. So no matter how you try to arrange it, by the way, this is a connected graph. So the original graph also must be connected. If at all this is a line graph or something, original graph is also connected. Now you see that, so if you take E0, E0 is adjacent to E1, right? So originally this is an edge of G, whatever this G is. So E0 is adjacent to E1, means it shares some vertex in common with E1. Similarly, E0 is adjacent to E3 as well, or E2 as well. Okay, so it shares a vertex in common with E2 also. Can it be this vertex? Suppose this is E2. Let's see, suppose this is E2. Then what must happen here? E2 and E3 must be adjacent, because here E2 and I'm sorry, what am I drawing? Missed it.
E1 and E2.
Yeah, E1 and E2 must be adjacent, because here E1 and E2 are adjacent, right? They have a vertex in common. So this cannot be true. So yeah, it must be like this, because there are only two end vertices for E0. So if it's not here, then E2 is here. Now where do I put E3? E3 also is adjacent to E0. So it has to be either this or this, right? But again, the same problem. If it's the first one, then E3 and E1 must be adjacent, which is not true. If it's the second one, E3 and E2 must be adjacent, which is also not true. So, see, simple way to see impossibility. Okay, but you can take a larger graph and ask this. And then there are other techniques to characterize whether it's true or not. Okay, check whether it's true. Okay, so now again, to relate it to matrices. So when you look at vertices and edges and their relation, you can define what is called the incidence matrix of a graph. So this is again a special case of a general definition. If you have any two sets S and T and the relation between them, okay, then you can encode that relation as a matrix with the rows indexed by S, columns indexed by T, and particular entry is 1 if that element of S is related to that element of T, and otherwise 0. Okay, so usually you call this relation an incidence relation, and this matrix is the incidence matrix. So you can define for any structure like that. When you have statistical designs, you have those blocks and incidence structures, right? There also you have blocks and points. There also you have this matrix. Okay, but here we will talk about the vertex edge incidence matrix, which is the default incidence matrix for a graph. So you simply say that in a graph, vertex, as I said, E is incident to or with V if E is of the form UV or VU symmetrically. Simple definition. So to get the incidence matrix of a graph, what you do is you index the rows by vertices, columns by edges. The number need not be same, m edges and n vertices. Let's say this is a matrix of order n by m, where n is the order number of vertices. and M is the size, number of entries. And again the same thing. The ij entry is 1 if and only if the edge ej is incident with the vertex vi, or vi is an end vertex of ej. Okay, so vi is 0 otherwise. Okay, so yeah, take a quick example.
Select between the pages.
Mhm.
You can't select between the pages.
No, that's
Should
one
be-
one page. I mean, that was in one page. Okay. Because I need to label the vertices here. That's edges here. That's about. This is, by the way, the 0, 1 incidence matrix. Another one is 0, 1, -1 incidence matrix of oriented graph. I think you may see that in one of the lectures, but I'll just discuss 0, 1 now. Okay, so 1 is incident. Okay, what is a simpler way? You look at the edges and write down which of the vertices they are incident to. Instead of going row by row and looking at the vertex and all the edges, it's easy if you look at edges, because edges will be incident with exactly 2 vertices. So E1 is incident with 1 and 2. Done. E2 is incident with 2 and 3. E3 is incident with 2 and 5. E4 with 3 and 5. E5 with 1 and 4. E6 with 4 and 5. Okay, that's it. And you can fill the remaining entries as zeros. Wait, is there something? Oh, no, that's not it. Okay. Again, what is the basic information that is present here? If you look at each column, what is true? Column sums are 2, because every edge is incident with exactly 2 vertices, whereas the row sums are the degrees, because every vertex is incident with how many edges? Equal to its number of neighbors, because in simple graph, as I said, that is the same. Correct. So the row sums give you degrees, column sums give you 2, and this gives you another proof of handshaking lemma, because if you take the sum of all entries, you can either interpret it as sum of the rows and their sum of the row sums, which gives you sum of degrees, or sum of the column sums, which is twice the number of columns, which is twice the number of entries. Okay, that's okay. But what will you get if you do B transpose B? Something related to line graph, let's see. So first of all, what will be the index? I mean, the rows and columns of this matrix will be indexed by what? Edges, because we're taking B transpose B, right? We won't do the full computation, just enough to get the idea. So let's see, what is the 1, 1 entry? 1, 1 entry is when you multiply a matrix with its transpose, what do you get? The ij entry is going to be dot product of ith and jth columns or rows. Columns, yes, because you're taking transpose, yes. Ith and jth columns. So in this case, ith and ith column, first column with itself, that means simply the norm square. So that is again the number of ones in that, right? So it's going to be 2. Whereas 1, 2 will be dot product of first and second columns means what? Yes? Number of entries where the or number of indices where both entries are 1 corresponding entry. So here for 1 and 2, these are both. Oh, sorry. Okay, we should use pointer. So these are both 1, right? Everywhere else it will be mismatched 1, 0, 0, 1, or 0, 0 anyway 0. Okay. So only this will contribute 1. Everything else 0. So you get 1 here. Okay. You get 1 here. Symmetric, obviously, if B transpose B symmetric. 1, 3 and 3 will be again 1 and 3. Is there anything matching? Yeah, this one again, the second entry, right? Again, second entry. This is same, and nothing else can match. Why? Because when will two columns have a common entry 1? If EI in EJ, those columns have the common entry 1, that means EI is incident with some VK and EJ is also incident with that VK. Can there be more than one such common entry? No, because then you would have parallel edges, which is not there, right? So the dot product of two distinct columns is either 0 or 1. It's 1 exactly when both of them are commonly adjacent to one vertex, right? So then it will be only 1 or 0, and the diagonal entries will all be equal to 2. Okay, so if you take B transpose B minus 2i, 2 times adjacency matrix, I mean identity matrix, sorry, you will get 0 as the diagonal entries and 1s and 0 as the other entries. So this is some adjacency matrix, but what adjacency matrix? That of the line graph, because when EI and EJ are adjacent edges of G, in this new graph represented by this matrix, the IJ entry is 1, which means ith and jth vertices are adjacent, right? And 0 otherwise. So that means it's a new graph where the vertices are edges of the original graph and ith and jth vertices are adjacent if and only if ith and jth edges are adjacent in the original graph, which is our definition of line graph. Okay, so this is the adjacency matrix of the line graph of G. Okay, yeah, I think we'll stop. Thank you. If you have any questions, you can ask later also. Trees and all I didn't cover.
Okay, thank you so much for today's patience. So we'll expect the same session tomorrow onwards. Okay, so tomorrow 9 a.m. we'll meet here. We'll start at 9 a.m. So 8:45 the bus will stop. Okay, yeah, thank you. Yeah, important for the webinar. Ladies can have they're not there. No, girls have some girls are taking very not in 13th class. Some girls are taking. Yeah. I mean Cookies arranged in a common place or different for girls? Oh, there, I got it. That is the reception. Because 11, you are going to say, you have to come to the second. Okay. Another was. Two different places. Upon same, no? Those were saying the 11th and in fact from the 13th. Those were saying the 11th. I am not right now. Not here by booth. I'll help you. Yeah, upstairs. Okay, I think I have to leave now. Yes, they will drop them now. For the dinner, we have arranged the TT. Okay. You can answer that. Just. TT is how big is it? That will accommodate. Additional. No problem. Just take care of this. Anything they are also staying there. No, I am in the circle. Actually, no, even he is joining. Yeah. It will come for. If my wife is ready, then I'll join. Yeah. So other married people are like this. You will also become like that only. Don't worry. Vinay, are you coming? I think there are. Vinay, you are staying in which block? You are staying in. You are coming? Bus is there. Bus is waiting. Anyway, we are going. Let's see. Okay. See you tomorrow. Yeah. Go the competition. What is your plan now? I have to drop.
Hello.
You can have it. I have to drop.
Hello, gentlemen. No, your your father is coming.
Now then we'll go. You don't see. Like we will drop them and then we will go. Where is Krishna? He just, I think, he gone down, sir. We'll go. He is supposed to carry this water bottle. No, we should leave. No, we will drop Ram Krishna Das and come back for coffee.
Huh?
Are you going to drop in? I mean,
Yeah, it's for me.
are you going?
Where is Naren?
Are you?
But you want the cabbage.
Are you going with him to drop the?
What? Oh, yes. Okay. Oh, it's not for me. Is it?
Huh? No. Where are you going?
Huh?
Can we? I have cycle. Usually have coffee together. So you are separate. Okay, you people can.
We'll go.
Sri Ramakrishna is not having coffee.
Huh?
Sri Ramakrishna is not having coffee. Is it?
No.
You might want to. We'll check. It is down. Okay. You have to give it again. Huh? Okay, let's check.
See.
Hey, you people have to either decide.
Is he not coming for coffee?
He might be, but he have to ask him now first.
We have to ask him.
We have one more vehicle.
I want to sing on this.
Harley Davidson is there. Come, let's go.
Where are you going? Buy or something?
Okay, after.
I can try. If you are doing it, I will also try.
Hey, you want to take? Okay, we'll go and come back.
Where?
Let's go. Let's go. They are waiting. See, Armugam sir has already gone. Armugam sir. So only Surang sir. Yogi sir. Where is he?
He is in the meeting. He was in the meeting.
Okay.
Below.
Okay. You people decide something and then.
He will take Sri Ramakrishna. Others let them go there. You can take yours. I can take mine. Let's go. What's the problem? There are only 5 of us.
No, then I have to take my cycle. I will not going to come back.
Why not? Come back and go.
No, I
Take
have
your
to
cycle.
basically buy so many things. I mean, so many at least tomorrow's food.
Come back and go.
Why are you?
No, we'll come back here.
Where are you going? Actually, tell me the location.
They'll close us.
What is the location?
Coffee.
Coffee location is what?
Shanti or bhai?
Then I can go by cycle. Why should I?
Okay.
Okay.
No.
After so many fails of auto, actually got frustrated.
He gave me easy. Easy. Easy for budget. I thought he gave you some certificate for living. Sounded like it. Student got easy. He gave easy. What and I have to take? I have to take the memory card.
It is so cold.
Don't forget to take the memory. Everything else can be here, no?
Yes.
ನೀವು ಹೇಳಿದ್ ನಂಗೆ ಗೊತ್ತಾಗ್ಲಿಲ್ಲ ಎಂತ ಅಂತ
What love?
ಮೈಕ್ ಇಟ್ಟು ತೆಗ್ದಿರ್ತೇವೆ
Okay.